Okay, so just recap real quick. So the domain, you take the argument and say that it's greater than 0. The range is never going to have any restrictions. When the graph looks like this, A is positive and B is greater than 1, and is the inverse of exponential growth. Bless you. All right, so this is what the generic form of exponential function looks like. A can be, A would be positive here as well. And then the base, if it's exponential growth, do you guys remember how you can describe the base of exponential growth? That's decay. So growth is going to be greater than 1. So it would look something like this. And then when we reflect that over the line y equals x, it reflects onto this shape of a logarithm. All right, and then whenever we have a logarithmic function, and that's in this form, and that a is negative, it's going to be reflected on the x-axis. And it is the inverse of exponential decay. Now, some people yesterday, when they were graphing the inverse of exponential decay, they got a little mixed up. It's just, for some reason, harder to visualize. Because I think it's because the inverses cross each other, and it feels kind of weird. All right, so when we have this generic form of an exponential function decay, a is also going to be greater than 0, but b is going to be between 0 and 1. All right, so there's this multiple choice question too, actually, on your assignment, and it's asking about the inverse of the graph. And so when you get to that one and you're just like, what's happening? Look back at those notes we took. I think you can figure it out. All right, and then the characteristics we're going to talk about is the domain and range. When a function is increasing and decreasing, the concavity, and the end behavior. And so one thing to keep in mind about logarithmic functions, they are either always increasing or always decreasing, which means you're never going to have these relative max or mins. It'll stay the same. There's no change. Same thing with concavity. The function will either be concave up or concave down always. So there's never points of inflection because the concavity doesn't change. And then the end behavior is what happens at the left and the right. What's different about logarithms is the left side. The x is not approaching negative infinity because it's the x's are not going to go past 0. So what you have is that on the left, you're approaching 0 from the right side. All right, and then to describe the end behavior on the right, you do go ahead and use positive infinity like always. And your answers to the limits are either going to be infinity or negative infinity because you are going to have one arrow pointing up and one arrow pointing down always on logarithms. Okay, so let's do some limits. So we're going to describe the end behavior, and Brian Passwater got you started on this first one. The left side, we are always going to have the limit as x approaches 0 from the right of the function f of x. So if we're going towards x is 0 from the right side, what is the graph approaching? Negative infinity. All right, and then the right-sided limit, you would write the limit as x approaches infinity of f of x. All right, and so what direction is the right side arrow pointing? Up to infinity. Very good. All right, so one of these will be negative infinity and the other one will be positive infinity, always on logarithmic functions. All right, so let's do another one. So the left side limit is going to be the limit as x approaches 0 from the right of h of x. All right, what do you guys think? Definitely positive infinity. Good. And then the right side limit, x is going to be approaching infinity. And then the right arrow is pointing down. So that's negative infinity. Okay. And then C is a little more challenging because we don't have the graph. But we can figure out which one of these is going to look like. It's either going to look like A or it's going to look like B. And to decide which one it looks like, you really just have to look at the number in the front. If it's positive, it's going to be the normal limit, or sorry, the normal logarithm shape. If it's negative, it'll be the upside down logarithm shape. So this one is going to be the normal logarithm shape. I drew it kind of wobbly. All right, so you guys write those two limit statements on your own, please. If you haven't already. Okay, so don't forget, there's three parts to limit statements. You have to have the limit, you have to have what x is approaching, you have to have the function, and then you have to have the answer. So you can't leave any of those parts out. All right, y'all good? Okay, let's talk about concavity. I feel like at this point, in AP Pre-Calculus, you can look at a graph and tell if it's concave up or concave down, increasing, decreasing without stressing too much. Hoping. So what do you guys think about A? Is A concave up or down? Up. So if it looks like a cup or a part of a cup, it's up. Increasing or decreasing? Decreasing, because if you were walking along, you would be falling. You would be going downhill. Okay, hold off before we go to the next one. It is possible that you might be asked a question a little bit differently. So another statement you could say is that this function is decreasing, which we already said that, at A or an, would the rate of decreasing be increasing or decreasing? At an increasing rate. Good. Well, if you were thinking of it that way, it is not getting steeper. So this rate of change, like this slope right here, would be like negative, I don't know, probably like negative 9, and then negative 7, and then negative 2, and then negative 1. So that is increasing. Those numbers are getting bigger. So the rate is increasing. But you don't even have to think about that. If you can just remember concave up is an increasing rate, and concave down is a decreasing. That's all you have to think of without even looking at the graph. All right, let's look at B. Concave up or down? Down. Is the graph increasing or decreasing? Increasing. So we could also say this is increasing at a decreasing rate. All right, and then for C, we have when we have to figure out the graph. So whenever the number in front is negative, it's going to look like this one. So I'm just going to draw that real quick. All right, So if you guys will circle the right thing and then write a statement underneath for me, please. Alright, so on example 3, they tell you that these are logarithmic functions. So we don't have to decide. We know that they are logarithmic functions. So what that means is the outputs are going to be evenly spaced, and you can go through and tell that they are. And then the inputs are going to be changing proportionally. There is a little bit of an exception to that, and we'll get to it in a second. So ones like the first couple, it's not super difficult to figure out the value of k. So on each of these, there's a number missing, and we need to figure out what that is. So when we look at the first one, what are you multiplying by each time? So what should k be? Yep. All right, for the next one, what are you multiplying by each time? So what should k be? Yep. So when we move backwards, you have to divide. Nice. Okay, and then this is the one that's kind of weird. Because when you look at these numbers, you're not multiplying by something each time. But it told us this is a logarithmic equation, or a logarithmic function. So what we're going to do, when you can't see the pattern, is we're going to find differences. And when we do, hopefully, we'll be able to see the pattern. So what happened is there is multiplication, but there's also some addition or subtraction in there, so it's hard to see it for a second. All right, so the difference between 4 and 5 is 1. That's 2. Unfortunately, that's the only pairs we have. So if I know this is logarithmic, I know we have to be multiplying by something each time. So what are you multiplying by? 2. So then we'll multiply by 2 again, and then multiply by 2 again. So what that means is the difference between these two should be 4, and the difference between these two should be 8 if this is a logarithmic function. So what k would make that happen? 11. All right, now, some of you see in patterns. Like I had a student last year that could figure that out in a second faster than I could probably. And some of you it might take a little bit longer. It's okay. It's just that's what some people's strengths are, and some people's don't have that strength. It's fine. All right, on this next one, we are multiplying by something. We're multiplying by a power of e, where when I multiply e to the second by it, I get e to the first. And when I multiply e to the 7th by it, I get e to the 10th. What do you think it is? When you multiply with the same base, what do you do with the powers? You add. So what are we multiplying by? E to what power? Yeah. So what should k be? Whoa. Yep. All right, y'all okay? It's okay. If patterns aren't your strength, you're going to be fine. Don't worry. All right, and then for example 4, we are going to find the domain and the range of each of these logarithmic functions. Now, I can go ahead and tell you what the range is. The range is all real numbers on a logarithmic function. So you can do all real numbers as negative infinity to infinity, or if you'd rather do this fancy r, you can do that. It's up to you. So it's easy. We don't even have to think about that. All right, and then for the domain, the argument, which in this case is x, has to be greater than 0. Now B and C are going to be a little more challenging. So when I go to B, the argument has to be greater than 0. So that just means x has to be greater. Whoops. X has to be greater than 3. All right, so you guys figure out the domain on C for me, please. Don't forget, the argument has to be greater than 0. You can call it negative 1.5 if you want to. Doesn't matter. But we can never take we can never take the logarithm of a negative or of 0. So that whatever is in those parentheses, that has to be greater than 0. All right, what questions do you guys have about characteristics?